So section 1.4 is all about building up to graph piecewise functions. So to do that, we start with a library of functions, which I like to call a menagerie of functions. So starting at the very beginning with the most basic of functions, here we have our constant function. This is f of x equals c, where c is a real number. Its domain, remember that's all its possible x values, goes from negative infinity to positive infinity. And its range is just that constant, right? So here, maybe this is the graph of f of x equals 3/2 is what I think it is. So that's a constant function. It's an example of a linear function. We also have the identity function. This is kind of the most basic linear function. This is when f of x equals x. So that means if I have x is 3, y is 3. If x is -2, y is -2. Remember, this is an odd function in case we're carrying over from section 1.3. And its domain and range for the identity function and the majority of linear functions that are not constant is going to be from negative infinity to positive infinity. So linear functions are typically written in the form f of x equals mx plus b, where m and b are real numbers. Remember, m is the slope, b is our y-intercept. And these can have positive slope, negative slope, or constant slope. So these are the three different types of linear functions we're going to see. After linear functions, we have the squaring function, also referred to as a parabola. This is the most basic of squaring functions. It's f of x equals x squared, and it is obtained by taking every x value and matching it with its square. So -1 goes to 1, 1 goes to 1, 2 goes to 4, and so on. So its domain goes from negative infinity to positive infinity, and the range of this specific function goes from 0 to infinity. This specific function is also even, right? It is symmetric across its y-axis. But as we start to move parabolas around our coordinate plane, they aren't always going to be even, and their range is what changes. But their domains from negative infinity to positive infinity. That is a truth. So quadratic functions are written in the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers, and a can't equal 0. They can have two possible zeros or solutions, right? If their vertex starts below the x-axis, they can have one solution, or 0 if their vertex is on the x-axis. And here, as you can see, the domain is still from negative infinity to positive infinity, but the ranges have changed. The range in this case goes from negative infinity to 0. The range in this case goes from, I'm going to say that's -4.5, -4.5 to infinity. Best guess is our range, but the domain never changes. And last but not least, it can have no solutions. That means our graph doesn't cross the x-axis. That means it has complex zeros. Complex zeros. And we're going to keep talking about all this stuff as the semester goes on. I just want to make sure everybody is aware, and it's not the first time we're seeing these things. Next, we have our cube function, right? Our cube function is defined by f of x equals x cubed, and it raises all values to their third power. Cubic functions have a domain of negative infinity to positive infinity, and their range is the same, right? Because if I cube a negative, I can get a negative number back, right? So this is our cubing function. This is an example of an odd function. Remember, not all cubics are odd, but this most basic one is. Next, we have our square root function. This is defined by all the real numbers it's not defined for when x is a negative number, right? We can't take the square root of negative numbers. We're working in the real world. So its domain goes from 0 to infinity, and its range goes from 0 to infinity. We're going to learn in section 1.5 how to shift these graphs around the coordinate plane. But for now, its domain goes from 0 to infinity, and so does its range. We also have the cube root function. The cube root function f of x equals the cube root of x. is defined for all real numbers, so its domain goes from negative infinity to positive infinity, as does its range. And this works because we can take the cube root of negative numbers. We also have the reciprocal function. This is a rational function, meaning it's expressed as a ratio. If f of x equals 1 over x, this is our rational function, and the domain in this case doesn't equal 0. Remember, for rational functions, we always have to set our denominator equal to 0, and that once we solve that equation, will tell us what values to exclude from our domain. The absolute value of function, defined by f of x equals the absolute value of x, is a function where each output represents the distance to the origin on a number line. Remember that absolute value is positive. So the domain is all real numbers because we can take the absolute value of every real number, but because the output is always going to be positive, the range goes from 0 to positive infinity. Last but not least, we have the greatest integer function. It doesn't come up very often, but I have to mention it. It's denoted f of x equals like these weird double brackets, or f of x int x. And what it does is it assigns the greatest integer less than or equal to any number in its domain. Okay? What does that mean? Well, 5 goes to 5. But negative 2 would go to negative 2, and 0 would go to 0. But if I have 6.45, that's going to go to 6. So for example, if I have 4.5, that's going to go to 4. If I have 4.3, that's going to go to 4. If I have 4.999, that's going to go to 4. It pushes it down. Okay, for negatives, it's the same. If I have negative 1.7, that's going to go to negative 2. We push it to the next integer lowest than it. If I have negative 3.5, that's going to go to negative 4. We push it down. So that's the greatest integer function.